Thank you. And I would just we will start with that for more or less 1 hour, and after we can have some tea. And just before, just to end this presentation, and after we'll see a little bit in more detail, maybe also in a more complicated way, a case study, which is a Cenomanian-Turonian anoxic event, which was probably for this kind of anoxic event the biggest one. And we talk about the stratigraphy, sedimentology, and geochemistry of that event. And we will talk also, because this is also an important thing, the role of phosphorus in this kind of events. And especially we will talk about phosphorus regeneration that you have here. If these things want to here, oops, here. And after we will see a little bit more about the problem of productivity versus preservation of organic matter. And we'll talk a little bit about that, because I think it's an important topic, especially for petroleum exploration. And after we can have a few conclusions. Okay, so let's start with the introduction. Okay, what is a black shell? And here, you have a view of black shell, which is not very black anymore, but this is due to alteration. And this is this kind of things that you can have here. Clearly, you can see that you have very nice lamination, and there is clearly an absence of bioturbation. So it's a very finely bedded shell, which is generally black, as you can see here. This is a thin section on the microscope. But you can see there is some layer which is very rich in organic matter, and some of them are a little bit enriched on planktic foraminifera. But you can see a very nice lamination, okay? So it means that it's some kind of an anaerobic accumulation of sediments, and which are enriched in organic matter. And the condition which is clearly essential for that would be the long-term depletion of oxygen in the marine bottom waters and into the sediments itself. This anoxic condition can be have two more or less main way to be. It's a widely restricted water circulation, or extremely high rates of phytoplankton production in surface water, or maybe a combination of both. Okay, so formation of marine organic rich sediments, namely black shell. We call a black shell for the geologist, especially for the petroleum geologist. These are sediments which have generally more than 5% organic matter, meaning that for petroleum exploration, this is a very good source rocks. I just remember you that, thanks to the black shell, we have, links to the black shell, we have the best probably source rocks in the world, mainly Jurassic and Cretaceous. Some of them also Paleozoic, but they are less common. And this is clearly an important thing in petroleum exploration, because, as you know, you need a source rocks in order to form petroleum, meaning that you need to more or less bury your organic matter and to transform this organic matter into kerogen. And towards, in order to do that, to transform your kerogen into oil or gas, what you need is clearly a little bit of increase of temperature. So you need to bury your sediments and at around 60, 70 degrees, meaning that you have to bury your sediments over at least 2 kilometers. It depends depending evidently from the geothermal gradient. But if you do that, you will transform your organic matter into oil and gas. Generally, The organic matter of marine or lacustrine origin is giving good oil, and the organic matter of terrestrial, coming from the plants, origin is giving generally gas, okay, because the first one is enriched in hydrogen and lipids, and the second one is more enriched in oxygen. So this is clearly one of the good reasons was why so much work has been done on this black shell, because from, let's say, Arabia Saudi, all these countries, to Venezuela, US, you more or less, all the big source rocks are linked with this kind of events. So the question here is as the following. Under which condition organic rich sediments are formed? Are they formed because of high productivity or because of good preservation? This is the big problem, and probably both, as you will see. Conditions particularly favorable to the formation of organic rich sediments, such as during a global anoxic event, do not exist today. That's for sure. Actually, we don't have really a place where we are forming this black shell. We have some locations which are depleted in oxygen, especially linked to upwelling activity with nutrient-rich water, like, for example, in the coast of Peru. But we don't really have this huge accumulation of black shell occurring. But I will show you that after, maybe in the near future, we may have this black shell accumulation occurring. Okay. So now, in fact, there is two models in order to produce black shell. Here, this is the first model, what we call more or less the productivity model, and it's this models is linked to the fact that you have areas of very high production, which are sustained by very high nutrient influx from upwelling, from more or less deeper water, but also from river or Ilion input, for example, very high export production rates. And by this way, you start to form an oxygen minimum zone. And clearly, you have the formation or deposition of organic rich sediments at the center of this oxygen minimum zone. And this oxygen minimum zone may move clearly onto the shelf, for example, if you have a transgression. So I would say it's some kind of dynamic models. And after you have the second models, which is more a stagnant model, a preservation model. So generally you have a semi-enclosed basin with a quite restricted circulation, okay? Some stagnant water, anoxic water, bottom water, preservation of potential is quite high. It's been postulated that global anoxic event, ocean circulation became very sluggish and bottom water were stagnant and anoxic. So you can extrapolate that for a xeristic basin to the entire ocean, for example, during the Permian Triassic mass extinction that we have seen. This preservation model is probably one of the best explanation for the black shell deposited during the Cretaceous, but not only. It's probably both of them. The best example for this preservation model is the Black Sea. As you know, the Black Sea is located here. You have the Turkey, this is Greece, and you have after Romania, after Bulgaria, Romania, Ukraine. This is a restricted basin, and there is only a very narrow strait here through the Bosphore, permitting some kind of, let's say, connection. But this is a very restricted basin. And here what happens generally, you have some rivers, big rivers coming in, and what you get is some caps of fresh water here. This fresh water will create some kind of boundary that we call chemocline or autocline. The autocline is the boundary where you have oxygen and less oxygen below. And so in this case, all this part will be under anoxic condition. And you will clearly preserve a lot of organic matter in this kind of environment. And this is the actual things that we have in the Black Sea, for example. So in the Black Sea, actually, in some place, you can preserve from 3 to 20% organic matter, total organic carbon, if you want. Okay, so it's quite interesting to see that. And after, the main question is also the preservation versus productivity. And here, generally, it's clear that you form organic-rich sediments when you have high production, okay? But it's not necessary to have always anoxic condition. But whereas in a preservation model, from the Black Sea model, you really need, it's an obligation to have anoxic condition in order to get organic matter, higher production. So how do you infer this more or less the degree of oxygenation in sediments, in the fossil examples? So here, for example, this is just a classification where you have the environmental oxygen levels with anoxic condition, suboxic, desoxic, and oxic condition, and these are the values of dissolved oxygen into the water. And you get some biophases, and some biophases, there are some appellation here, some term, anaerobic, disaerobic, and aerobic, okay? And this is more or less corresponding to anoxic, suboxic, desoxic, and oxic condition. Here, well, you can add the term, in this case, to oxinic, meaning that, well, you have reductive condition, low oxygen condition up to the surface. Oxinic is coming, it's a name coming from the Black Sea. This is the name of the strait that you have in front of Istanbul, the Pont Euxin. So it's a lot of examples have been taken from the Black Sea, which is actually the modern example for a stagnant, restricted basin where preservation of organic matter is really important. Well, if you go to the field, because you are a geologist, and well, you have to look at the rocks, and you have many ways to have an evaluation of this kind of oxygenation level. And it's especially, as I said before, linked to the intensity of the bioturbation. So in a very low condition, oxygen condition, as you have here, for example, in anaerobic condition, you can see that you will get pure laminated sediments. And on top, on the seafloor, you have mats which are produced by sulfur bacteria. And if you increase the average of oxygen on the seafloor here, in the rocks you will have more and more bioturbation. First of all, in a very disaerobic condition, you have just a little bit of bioturbation at the surface. Very small animals living, and generally they are bioturbating the surface, and they are not going deeper. And if you go with more and more and more oxygen to aerobic condition, you can see that you increase the size of the tunnel of the bioturbation and the size of the animals which are responsible for this bioturbation. So if you look to rocks, you can be evidently able to decipher the intensity, the degree of oxygenation by just looking at the ichnofacies, okay? So it's a good way, very simple way, and very cheap way. You just go to the field and look, for example, in this case, well, so you have a decreased bottom water oxygenation to the right, and here you can see that we have only a few chondrites. It's a name for a small bioturbation, which are probably linked to worms or things like that. And these animals are living at the surface and just burrowing a little bit because very, very quickly the sediments is really too anoxic in order to live in, okay? And after, you can see that the depth of the biotubation is increasing when the oxygenation is increasing, because these sediments is less anoxic inside, and you have more and more life at the bottom, okay? So it's a way to measure the degree of oxidation. And another way that we just talked, and that's why 2 days ago I was explaining that I will give you better examples. If to use also, and here you need a microscope clearly, and an electron microscope will be still better, but you can do this with a good microscope. It's to check what we call the pyrite thromboid. Okay, what happens generally? In an anoxic environment, very anoxic environment, in the water column you have a lot of productivity, a lot, for example, of foraminifera, planktic foraminifera, and you know that the planktic foraminifera is sometimes coiled and has some chamber. And if you have a lot of organic matter and a lot of an anoxia coming into more or less this water column, not only on the seafloor, what will happen that you will have a degradation of the organic matter in the water column by this sulfite bacteria, which will transform organic matter and produce some pyrite. But this pyrite is very small, because generally this pyrite is formed into the chamber of the very small planktic foraminifera, for example. And they have this thromboid morphology. And here you can see that this is a study which has been done on some Permian Triassic by Winglal. And you can see here, for example, that these are cherts. What a chert is radiolarian-rich sediments. This is a section from Japan in the middle of the Pantalassa. This is examples that I took for the Permian Triassic mass extinction to explain to you that almost all the global ocean was under anoxic condition at the Permian Triassic mass extinction event. And you can see that in this chart, pale gray, not dark, they don't have any thromboids. And suddenly here we have some thromboids arriving. And generally, what these thromboids have that kind of morphology. As you can see, they are quite nice, and they are small. And it's very important to measure this thromboid. You can see that these ones have 5 micrometers in diameter, which is very small. And this is generally the diameter of the chamber of any kind of foraminifera, for example, living in the water column, which is full of organic matter, and this organic matter will be in situ degraded into this pyrite, into this sulfur. Generally, I said yesterday, if you remember, that in the sediments you have at least 1 meter below, always generally reduced condition, because whatever it is, you have less oxygen, more bacteria, but the thromboids that you will produce by this system are bigger, a lot bigger, more or less 20 to 50 microns in diameter. So the best way to more or less say that the water was anoxic is just to measure this kind of thromboid here and to count them and to see a little bit if you see an evolution. And here clearly this is full, and this is really indicative that you have a black pyritic black shell deposited under fully anoxic condition, maybe oxenic condition. Okay, so now this is a way where there is different way. As you will see, I will show you different way to perform this kind of analysis. This is a way that you can do simply on the field or under microscope. Clearly, you can use geochemistry, and we will see this later. But no, in fact, we have to define a little bit what is more or less global anoxic events. So this is quite simple. As you can see here, this is an episode during Earth history during which the formation of organic rich sediments is quite widespread, meaning from it's not local, it's really global sometimes. Sometimes linked to mass extinction, but sometimes not so much, as you will see. And in much of the case, the duration is quite short. You can see it's around 500,000 years maximum, sometimes a little bit less. So, well, there is an exception, clearly. This is the Permian-Triassic mass extinction, where anoxic conditions were prevailing during at least more than 1 million years. Generally, clearly you have a lot of organic matter, and the black shell, I remember you, this is a sediment by definition, which is a shell with not so many carbonate, and a lot of organic matter, more than 5%, okay? And afterwards, well, generally, you will see that this black shell deposition are generally connected with, correlated with some huge marine transgression. Why? There is probably 2 reasons. First of all, when you have a transgression, the sea level coming onto the shelf, the shelf will be remobilized, and a lot of nutrients will be remobilized, so sustaining high productivity. And the second things, well, you need, in order to have black shell deposition, to have, let's say, some, quiet environment, because if you have storm, tempestite, clearly you will oxygenate the seafloor. So in order to get maximum productivity, you need quite a huge transgression, which allow generally to the placement of location where sediment deposition are made of very fine grain deposited in a very quiet environment. You will not find black shell, or very rarely, at 10 meters depth. It's impossible, because you have storm deposits, you have current. All these things will destroy the sediments, oxygenate the sediments, so it cannot be the case. So generally, you need a minimum depth in order to form black shell. And I would say this minimum depth would be around 200 meters depth. Why? Because this is a limit where tempestite may influence and rework the sediments, okay? So this is one point. The second point, they are often associated with positive excursion in stable carbon isotopes. It's very easy to understand. If you increase the productivity, it means that you will increase the consumption of the isotope 12 by the organism, which preferentially are more or less doing that. So in the ratio, you will increase the delta C13 ratio. So generally, you will see that a lot of these increasing productivity events are linked to positive carbon excursion. Contrary, when you have a mass extinction, for example, a crash in productivity, no more organism, you will have a negative excursion, as I said yesterday. But you can also, I remember you, have negative excursion linked to other phenomena which are not linked to the biology, but linked more to increasing CO2 or increasing the methane hydrate into the sea, for example. So it's not always so simple, but generally you will see that we have a very nice positive excursion when we have black shell deposition. If you want a lot of productivity in your sea, you need to increase the precipitation, because under warm condition. Why? Because if you have warm condition, a lot of precipitation, you will increase the leaching of the rocks by the rain, and by this way, you will weather the rocks and made a lot of, let's say, elements which are very important for boosting the productivity. The first one, and we talk about the phosphorus this afternoon, quite a long time, is phosphorus, which is really one of the biolimitant elements. It's really necessary for life, but it's not the only one. There is also some trace elements which are very important in small quantity for the organism, like the cadmium. If you have too much cadmium, it's become a poison, clearly. But we need that. We need copper, we need zinc. All these bio-limited elements are very important for life. But phosphorus is probably the most important. In many cases, as you will see, these black shell are related, these anoxic events are related to major volcanic phases, large igneous provinces, but for the one which are really linked to increasing productivity, they are generally linked to some major province which are submarine, as you will see. And that's why, for example, during the Jurassic or the Cretaceous, you had at least 4 or 5 of these global anoxic events, but these events doesn't really lead to mass extinction. There is maybe a little more extinction, but generally for the Somalian-Turonian boundary, as we will see in detail, the origination, the new species, are more or less exactly the same as species disappearing. So it's not really a period where you have mass extinction. In order to have some mass extinction, I think you need some bigger trigger, like huge continental volcanic activity or a meteorite impact, for example. And as I said, I will show you a graphic later on. It's a major oil source. Without the black shell, I think, well, it would be difficult to drive your car, because this is the source of the petroleum of many rocks. So that's why we name these fossils energy, because, well, in order to produce a black shell, you need millions of years. Don't forget that. And this, you cannot renew this more or less reserve of energy in 10 years. It's impossible. And this is a problem that we will face later on. Okay. Now I will just want to show you, to list, in fact, one of the main global anoxic events in Earth history. So there is some Paleozoic one, which are less known, I would say, but they deliver quite a lot of oil and gas. Silurian, the graptolite shales, I will go back to that later on. Some Silurian, so it's Paleozoic. Late Devonian, the Kelvasser event sometimes may deliver some oil and gas, because they are quite well distributed all around the world, and this one corresponds to mass extinction event. Some in the Permian, but after we have especially the one from the early Jurassic Toarcian, the Posidonia shale, so the Toarcian, the late Jurassic Emergian, which are quite important also in England, in Siberia, in Mexico. And we have the Cretaceous one. And the Cretaceous, we have quite a lot of this anoxic event. For example, here, and also in the Coniacian-Turonian for what is Cretaceous. And we have maybe a last accumulation, maybe the only one, which is tertiary, which lead to some oil accumulation also. This is Miocene Monterey Formation in California. So you can see we have a lot of this black shell, but main part of the black shell are from Jurassic and Cretaceous time. Okay, so doesn't work anymore. This thing has a problem. It's a bit strange. Okay, so just a few examples here. We have, for example, here, this is a Silurian graptolite shell. Excuse me. And this Silurian graptolite shell, as the name is made of black, let's say, shell, but which are quite full of these quite strange animals. Graptolite, we don't really know what phylum they more or less are from. It seems to be maybe an ancestor of an hemichordate, we don't know. But this was like that. They were floating in the water, and in the rocks, in fact, what you see is this kind of a segment like that. The Silurian graptolite black shell were quite producing quite some oil. Here we have seen that 2 days ago. Devonian Calvasser horizon, equivalents from Germany, Morocco, and USA, and also these two black shell events, which also are very well distributed. In the Permian, we have also in the Permian, we have also a layer which contain up to 20% of organic matter. You know how much organic matter do we have in a normal rock? Just to give you an idea of what means 20% of TOC, total organic carbon, in a rock. You know, in a normal sediment, the average, more or less, mean of TOC content in a sediment is almost nothing, 0.1617. So it's clear that it's a big difference compared, for example, to this black shell, which were extending from England to Germany during the Permian, and they have more than 20% TOC content, which is really, really a lot. And now we can see something that I showed you this morning. This is a Toarcian Positania shell. So these are really very nice black shell, very well known because they contain very well preserved fossils, like this ichthyosaur, marine reptile fossils, plesiosaur, but a lot of ammonites also. And these Toarcian black shell are known from South America to Europe. There is quite good distribution of this black shell. Here I just show you two slides from one former PhD student, Alicia Fantasia. And by the way, she did a master. The topic of his master was here in India about intertrapen of the Deccan. And after she moved to the Toarcian for her PhD thesis. Okay, here I just want to show you a few things. It's a study that she have done for this PhD. She went, in fact, to different basin close to Switzerland, the Alpine Tethys, into the Lusitanian Basin in Portugal. She was also working in Chile. We went into Atacama Desert in order to compare all this basin. And here there is things also in yellow that you can see here. This is Carophera, large igneous provinces, volcanoes, continental volcanoes, terrestrial volcanoes, which were probably more or less a trigger of this Toarcian event. So you can see here, this is a section in a borehole in Switzerland, that this Toarcian is very black from time to time with laminated sediments. And what we have done here, for example, is to measure the TOC, the quantity of TOC, but also the more or less the nature of the organic matter. And here we call this rock eval analysis, well, rock eval analysis are also done by ONGC people. I saw a machine very, very long time ago in China. The rock eval analysis allow you, in fact, to separate the organic matter, to have an idea of the quantity of total organic carbon that you have in your rocks by just eating your rocks, and you are measuring different things like the monoxide, carbon monoxide, the carbon dioxide, and the quantity of organic matter. And here what you have is an index, which is an hydrogen index. And here this is an oxygen index. If you have a very high hydrogen index, generally, and low oxygen index, it means that the organic matter is very rich in hydrogen. This is like some people may know that the Van Crevelen diagram, which is using just the element, oxygen and carbon. But here we are using these kind of things. And when it's high, it means that your organic matter is marine or lacustrine, and the oxygen is low. It means, again, that it's marine. If your oxygen here is increasing from 0 to 100, 150, and lowering more or less hydrogen index, it means that this is terrestrial, type 3 organic matter. And if your oxygen index is high, like that, it means that your organic matter is not very well preserved and starts to be degraded by oxidation, preservation of organic matter. So it's a measurement which gives you the total of organic matter, the nature of organic matter, lacustrine, marine, or continental, but also the preservation of organic matter. And here it's interesting to see that more, and this has a green point here, more of these green points are more or less turned to the right part of the graphics. It means weathering, oxidation. More they are on the left part, it means generally better preservation. And here the green points are coming from an outcrops outside, where alteration can be quite high. And the red one are coming from a borehole. And you can see here that generally you have a better preservation into the borehole than in your outcrops. This is quite normal because you have some oxidation on an outcrops that you don't have into a drill core, okay? And we can also measure with that machine different things against this hydrogen index, but versus measurement, which I don't want to go into details, but will give you more or less the degree of maturity of your organic matter. Because for the people looking at petroleum, it's very important to know if your organic matter is immature, so not transformed into oil and gas, if it's mature, transformed in oil and gas, or over mature, meaning that already everything has been transformed and everything escaped, okay? So it doesn't matter, it doesn't look very interesting to follow more on exploration if you get this data. And here you can see that all these points give you an organic matter which is quite immature. So it's not the place where you have to look for petroleum, for example, okay? So it's a measurement of preservation. And what she did also, and it's also to use trace elements to show a little bit more or less the degree of oxygenation, meaning that, or the degree of low oxygen condition, I would say. And here I told you that there is different elements showing more or less can be used in order to see the level of oxygenation of the rocks. Because, well, some elements, especially uranium, vanadium, molybdenum here, are generally linked to very low oxygen condition. Why? Because they are linked to reductive condition. They cannot be fixed under oxygenated condition. It's exactly the contrary as phosphorus. Phosphorus don't like more or less low oxygen condition because phosphorus is always fixed under oxide. And generally, vanadium, uranium, molybdenum especially, are linked to very low oxygen condition because they are fixed under very reductive condition. Nickel and copper generally are linked with organic matter, so it's a way to measure the intensity of the productivity, if you want. And here you can see that on that section, for example, that in the interval, this is a gray interval, you can see that nickel, copper, vanadium, molybdenum, and this as a black point, are increasing, okay? Okay, they can increase, but it's also important to know that the increase of these elements has to be also controlled, because the increase, well, could be linked to increasing, for example, decreasing sedimentation rate. If you decrease the rate of sediment coming into the seafloor, clearly you create a condensation of your sediments, and you will have some kind of an artifact of increasing vanadium or molybdenum and so on. So what you need is to calculate some enrichment factor. In fact, we compare this, we use ratio with aluminum, which is generally linked to increasing sedimentation rate or increasing detritism, and we compare that with the average mean for the Earth, if you want, average shale mean. And by this way, you can see that the name of that enrichment factor, and the name is easy to understand, okay? And you can see here that compared to the mean values, your vanadium and molybdenum is really enriched. And this tells you that these sediments have been deposited in quite anoxic condition. Okay, this is an example that we just did some yes, last year. So it's been published last year, and this is a nice way to infer, in fact, to use the geochemistry to infer as intensity of anoxy during this kind of interval. Another very nice black shale deposition. This is chimeric clays, as so the name is indicating. The chimeric clays have been deposited in England, but also in Mexico, in Siberia. And this is an end-Jurassic black shale deposition, which lead to a huge petroleum province, like in Mexico. And the next one, and here we'll spend a little more time afterwards, these are the Cretaceous anoxic event. And on that picture, I have, it's really a very nice picture, because on that picture you can really see on the field what is an anoxic event. So you can see here that you have a thin yellow, white layer, pure carbonate. These are pelagic carbonate. Doesn't mean, it means that they have been deposited in deeper setting. All this carbonate here are deposited in deeper setting, let's say 500 up to 1,000 meter deep. They are made only based on planktic foraminiferous and also nanofossils. It's very fine limestone. And generally, you know that it's very regularly deposited, meaning that probably there's a cycle which are linked to orbital cycle like the Milankovitch. And meaning that, you know, you have different kind of orbital cycle, but the main one means that the Earth is a little bit regularly, a little bit more far from the Sun. So while you have a climatic change corresponding after in your rocks to a change from if you have more arid condition, for example, or cooler condition, you have generally less detrital input, so you have pure carbonate. And when you change that to more insolation, more humid condition, you get the interval where you have a little bit more Mars. And it give you this repetition, Mars, pure limestone, Mars, pure limestone. This is really cyclic and depends to orbital parameters. But here, what you can see very clearly, that this very nice white pelagic limestones, very regularly deposited, are suddenly, several times, interrupted by some black layer. These are black shale deposited in quite deep environment. And here, this is the first one into the Trivian. You have a second one, which is really a huge one, known all over the world. This is the Option one. And you have a third one. This is the one that we will see in more details. This is the Cenomanian-Turonian boundary 1. And you can see here that they have name. These are local name, like you have a name for your formation in India, like the Arialo formation and things like that. Here they, for these very special events, here they give name to some geologists, in fact. So Bonarelli, it's an Italian geologist, Selli and Faraoni and so on. Because that section is in Italy. But it's really, it's a beautiful quarry, the Contessa quarry, where you can see a succession of this anoxic event, one after the other. Okay. The last one is Monterey Formation. It's the last example of an anoxic. It's the only one which really exists in the tertiary. And it corresponds, this is Miocene in age, and it corresponds mainly to the Californian coast, where you have a lot of upwelling activity, boosting the productivity. And here you can see that you have very nice laminated, but here you can see that this laminated bed are generally interrupted by whitish things. All these whitish things are phosphate layer. So now we have discussed largely about this anoxic event as major oil source rocks. And here I can show you on this this panel that that panel that well you have different. This is the proportion, the percent of world's original petroleum reserve generated by source rocks on a stratigraphic interval. Okay, oil and gas, and here you can see that the graptolite shale from the Silurian represents 9% of gas and some percent of oil. You have here, this is the upper Devonian Kelvasser that I just show you, and here clearly the upper Jurassic. It's almost 25% of more or less reserve. And here you can see this is the Aptian Turonian. So all the black shale that I show you on the last picture are more or less here on that graph. 30% of the world's original petroleum reserve. And well, this is the last one, the Miocene one. So you can see here that clearly black shale are responsible for the main reserve of petroleum in the world, and that's why well it has been so important to study them. Okay. Well, this was for general introduction, and now what we will see is a little bit in detail how do you form this black shale. And well, I will take the examples of the mid-Cretaceous oceanic anoxic event. And we will see in details, for example, the Cenomanian-Turonian one. Okay. This is quite a busy diagram, but very interesting, in fact, showing many things. And I will try to go in detail on that before the tea time. Okay, this is the age, 92 to 124, meaning that this is lower Cretaceous, upper Cretaceous here. You have the Cenomanian-Turonian boundary here, and well, you can see here several things. Let's start with that curve. This is a delta C13 curve here. In gray, this is a delta C13 curve based on carbonate, and in black based on organic carbon, which give you more or less the same. Meaning that the two reservoirs are concerned by this kind of events. So you can see here that we have some name, OA1B, oceanic anoxic event, and after this one, 1C, 1D, and OA2. So it's, and you can see that each of these anoxic events correspond to a huge increase in delta C13 here, for example, but especially here for the Cenomanian-Turonian one, okay? And well, this is quite important. Here what people put, we discussed this for the Permian Triassic mass extinction. You know, this thing is really not working. Mass extinction event, and this is a strontium 87-86 ratio, which generally indicate if we, in order to make it very simple, when this ratio is low, it means that you have alteration of basaltic rocks, a lot of activity, a lot of production of oceanic crust, which is made of mainly basalt, and the ratio is this one. And when you get something which is generally more positive, it's the increasing of the alteration of old basement from craton, which are located on continents. And it means that you have clearly a lot of runoff, a lot of weathering occurring on land. So, and here we put some, you can see that the Leckie et al., this is author of this paper, put some event here. As you can see in red, these are volcanic activity, submarine volcanic activity. So it becomes quite clear that there is quite a good correspondence between huge volcanic activity, mainly submarine, and more or less this kind of event. And I can show you the first one here. Sorry. This is Livello Faraoni in Italian, and which is just below here. It's not on that sections, but this is upper Ottovian age, and you can see very nice black shells here occurring in between two very white pure limestone deposited in oxic condition. So this is a sharp change to from oxic to suboxic and anoxic condition. And on top of that, you have a little bit higher. Here, this is Aptian event. We have a very nice delta C13 positive shift. And here, in some deep setting, so this is this sediment has been deposited in quite deep setting. You have occurrence again of huge black shell, which contain up to 20-25% of TOC. And the next one, here's the Cenomanian-Turonian, Livello Bonarelli, and again here, this is that one. You can see that in fact we have here some pelagic limestones, there is almost no red matter, and there is some change here. This color change corresponds to increasing radiolion-rich level, which means that before this anoxic event here we have a change in the kind of organism that you have, meaning that it's more and more productivity, and radiolarian like this increasing productivity. And after we have this black shell deposition, and again the white limestone corresponding to more oxy condition. So these are the story for this Cretaceous anoxic event. But in fact, the story starts a little bit before into the Valanginian. So the Valanginian, the stage is lower Cretaceous. We have here very nice positive excursion of the delta C13, which means probably that, well, you increase partly the productivity. And you can see that this corresponds to several biotic change, mainly decline in some nanofossils, for example, or decline in some foraminifera. So this was probably a prelude to that event, but it's probably not the main one. Okay, so now if we try a little bit to look in detail to that crisis, there is a good relation between, in fact, the climate and sea level, as you will see. Sea level is here, and you can see here, this is deposition of the black shell up to the top here, and you can see here that generally this corresponds to sea level high, and maximum sea level for this OAE2. So there is quite a good correlation between long-term sea level fluctuation and also the volcanism here. And well, the Cenomanian-Turonian OAE2, Ocean Anoxic 2, correspond to the highest sea levels known in the Phanerozoic. And it seems that the fluctuation here of the delta C13 is quite linked to this sea level fluctuation. This is normal because the productivity seems to be linked to increasing volcanism and consequently to increasing sea level. So it's a little bit what you can see here. And for example, this is all the Cretaceous time. You start here with the Berriasian. So this Jurassic Cretaceous boundary is somewhere here. And you have all the Cretaceous here. And what you can see, different curve, which is really interesting here. I can start with the crustal production. So this is the production of the oceanic plateau here, okay, here and here. You can see here, this is the global total crystal production. And these are the volcanic events. And you can see here that, well, you have for the Valanginian the Parana and Endeca, which is a little bit different, the terrestrial one. But after all these ones, big ones, are linked to submarine volcanism, what we know submarine plateau. And these are huge. Ontong Java is almost a continent in terms of surface of lava flow. And this is strontium, where you can see that during this volcanic strontium is quite low, and it's increased afterwards. Sea level we already discussed. This is generally high sea level, and here you have the oxygen isotopes, which allow you to measure the temperature of the seawater, and clearly you can see that this part of the Cretaceous was quite warm, with a lot of CO2. Okay, so this was a time of huge volcanic activity, huge crystal production, and the next one is a little bit more informative still. You can see this is a total of ocean crust production, and you can see that since the Aptian, where you start the OIA, all these are OIA, up to the Cenomanian, you have a maximum of oceanic crystal production, meaning maximum of activity to the mid-ocean ridge, so a lot of submarine volcanism. And you can see here, this the blue curve, is the paleo temperature, quite hot, and this is the sea level, quite high sea level, and the oil resource here. So it corresponds to a huge, clearly, oil resources, as you can see here. So this time clearly is crucial for that, and this is linked to this huge volcanic activity that we have here. So it's a map here where you have all the continental float basalt provinces, all the volcanic rift margin, but especially the blue one that you have to look here. These are the oceanic plateau and the oceanic basalt. And you have some age, as you can see here. So, for example, here, the Deccan, it's a continental one. We talk about that tomorrow, 66 million years ago. The traps of Siberia that we already talked for the PET permanent Triassic boundary. The camp, you have camp here, you have camp here, you have camp here. It's normal because before there was no Central Atlantic. This was a rift, okay? But it's a huge volcanic activity, as you can see. And let's go to submarine now. You have the Caribbean Columbian. The age coincide with the Cenomanian Turonian. So it coincides with the oceanic anoxic event too. And this is fully marine, okay? Submarine. And here you have a lot of submarine basalt erupting, as you can see, all more or less during the Cretaceous, during the time of OIE. And the biggest one is that one. This is the Ontong Java Plateau. This is like a continent, if you want, submarine continent, made of basalt, which was erupting during mainly the Aptian, Albian, and partly up to the Turonian. So there is a huge coincidence between the submarine basaltic flow and this oceanic anoxic event, which is clearly quite interesting. And the main one are, as I said, the Caribbean Plateau. The Caribbean Plateau, note that this is an actual map, clearly. The Caribbean Plateau during, was at the Cenomanian Turonian was somewhere there, and it was drifting here into Central America, creating here one of the most complicated geological areas that I know. It's just an accretion of terrains and terrains, very difficult to understand. And the next were clearly all this area with the Kerguelen and so on. And the biggest, really the huge one, as I said, was this Ontong Java Plateau, which is really huge. And maybe this is an explanation, because a lot of people are saying, well, you are talking about a lot of volcanism, but this volcanism is clearly behind the formation of black shale, but there is no extinction, or not so many extinction. Yes, because clearly it's a submarine. And the red one, especially the Siberian traps, the camp, the Deccan, are generally all continental. And these ones were lethal and were provoking mass extinction event. Okay, so now if we go, I will go in details. I will more or less, we will see more or less a little bit more in details the Cenomanian Turonian OIE2. This is that one here. And but I think we can make a short break, tea time, okay? Because I can just come on that one, and after we'll make a short break. So here again, this is a carbon isotopes curve. You can see that you have a very huge, it's several per mil, very nice positive excursion. This positive excursion means you have an increasing productivity. This is quite clear. And this corresponds, this is a different sea level fluctuation curve, a maximum of sea level that you have here. And here you can see that this one generally corresponds to some volcanic activity almost everywhere. So it's a project that we had some years ago. We worked some 10 years ago about the Cenomanian-Tuvorian boundary. And I will show you a lot of examples taken from, we will travel from Italy, Europe, Morocco, US, up to Tibet to see different sections. And I will try to explain to you a little bit more in details what happens during this time. Okay, let's stop for a while. we will start again. As I said, we will see in detail this Cenomanian Turonian black shell deposition, and well, we have already seen on that slide with this massive shift in delta C13, meaning don't forget that when you have this kind of change into the delta C13 isotopes, mean really that you have a huge perturbation of the carbon cycle. Clearly, as I said also some 2 days ago, this kind of let's say carbon sequestration, because what you do is you accumulate organic matter into the sediments, so this carbon will not go back to the Earth's surface and afterwards to the atmosphere. So it's a way clearly also to mitigate the warming, and clearly here generally you have short period of cooling right after this kind of event, which is quite normal. Okay, so now how we do that? How can we explain this kind of things? And here, first of all, you have to realize, to remember that volcanoes are generally, for main part of this volcanism, are submarine. And so the first things that they do, they provide to the sea a lot of metals linked to this activity, to the ridge. And you have clearly iron, nickel, cobalt, zinc, cadmium, and as I said, these elements or trace elements, depending, will boost the productivity, the biological productivity into the sea. Okay, and this may lead also to the black shell clearly deposition. This is one point. Another point is also the fact that part of the CO2 will go into the atmosphere, and it may increase the temperature and the rainfall, increase the greenhouse condition. You have more nutrient runoff, and you also this will participate to the boost of the biological productivity, leading to the deposition of black shell. Excuse me? Oh, I didn't see that. Sorry for that. Okay. Yeah, it's a lot better by now. So this is more or less the way that people like Larson and Erba are more or less seeing this kind of mechanism. Okay. Now there is several questions here that can be added. Okay, I fully agree that, well, if you consider all the basalt plateau, submarine plateau, this kind of mechanism must have been really important. About that kind, well, there is some question here. And here, maybe it's not only the volcanism, because CO2, you know, the ocean has a buffer effect, which is quite important. Meaning that, well, there is a dilution here, clearly effect. I'm not so sure that a lot of CO2 is coming into the atmosphere. But, well, maybe we have another phenomena like orbital forcing by cyclicity. So maybe this time of a huge volcanic activity were coinciding with a time where the orbital parameters were really, really well, more or less paced in order to produce more insolation, more temperature, and more rainfall. So it's probably a combination here. And by me, volcanic volcanoes may not explain everything. But what we will see here is the case study of the Cenomanian-Turonian. And here, well, we will talk a little bit about stratigraphy, sedimentology, geochemistry, and after we will end with the crucial role of the phosphorus for this kind of for the Cenomanian-Turonian black shale event. Okay, so now just a few things about this Cenomanian-Turonian anoxic event. So here, what you see, here's more or less the Cenomanian-Turonian boundary, and which is very well dated by biostratigraphy. You have some plantiforamnifera here, and especially, in fact, you have the disappearance. I will explain this in details, which is a very nice example of extinction, in fact, which is not so big. It concerns just a group of foraminifera, but a special group. As you will see, it's quite illustrative for the Cenomanian-Turonian anoxic condition. And we have also the nanofossils, which have this microscopic remains of algae, which also allow a very nice biostratigraphy. We have also some ash layer, bentonite, which are very good to date, as you will see later on. And we have the strontium stratigraphy, where you can see that this period is quite interesting, because right before, and don't forget that, it's very important, you have quite positive values indicative of increasing weathering on land, okay? Because it indicates that more or less the old craton are weathered, and shifting to clearly less positive values, meaning that here you have volcanic activity and probably the alteration of a large part of submarine basalt linked to the volcanism that we just saw. The delta C13 shift here, and this corresponds to a huge sea level rise, I said. And you can see here, in terms of the planktonic evolutionary events, there is not so much things. You can see that the appearance, disappearance is more or less the same. So it's not really a mass extinction, by far not, but there is some extinction occurring. Okay, so it means that clearly this is one of the most extensive mid-Cretaceous burial events, if you abstract that. High sea level Phanerozoic and intensive volcanism, as I said. It coincides with highest global warming during the last 115 million years, very hot as at that level. And we have a large positive global carbon isotope excursion in both carbonate and organic matter. And so it's really a major perturbation of the carbon budget due to extensive burial of organic matter of black shale due to this increasing productivity. And this burial afterwards, because you have a sequestration of the organic carbon, which is very important, may have led to 40–80% reduction of PCO2, and maybe below 500 pp V. And here, well, 500 is very close, but we know actually what is more or less content of CO2 in the atmosphere actually. You can see that on the website day by day. It's 415 by now. So, well, you can see. But during the event, this was a lot more higher, clearly. And clearly, as we said, the biggest source rocks for the petroleum. I just, well, there is a lot of let's say, producer which are linked to that event. Saudi, Arabia Saudi, Brazil, Venezuela, and so on. And as I said, it's a modest extinction. 7% of families, 26% of genera. In fact, the number of speciation, appearance of a new species, and the number of extinction is almost the same. Okay, just a small view here of this anoxic event. So this is in France, south of France, very nice cliff, and the Cenomanian-Turonian black shale are just here. You can see it's darker, more laminated. This is in Tunisia. It's a black shell just here, or black here. And this is in England. This is interesting here in England. During Cenomanian-Turonian, you have generally choke, which are interrupted by these marls, which are enriched in organic matter, the planus marls, which correspond to the same event. Okay, when I said it's not a major excursion, here, for example, you have the comparison of the Cenomanian-Turonian boundary, percentage extinction at a generic level. You can compare this with the Cretaceous tertiary boundary. Well, for some groups, this was quite elevated, which are linked to the benthic fauna, but you can see that some other groups, clearly, this was a lot less. So it's not really a major extinction. And now I can show you a very nice model from Jarvis et al. Mainly, some English researcher, micropaleontologist, and which explain you more or less how it works in terms of this extinction due to anoxic event. And well, this is, let's say, this extinction model it's a pre-extinction here stage. So what you have is very high diversity of microfauna in both benthic, as you have here. There is some ostracods, there is some benthic foraminifera, quite a lot. And we are talking mainly on microfauna here. And some planktic microfauna, which are also quite well diversified. One guys here, this especially this one, these two ones, belongs to a group, the Rotaliporridae, which have an interesting, more or less, cycle life. Meaning that during the cycle life, they go down and go up, down and up. So they are traveling through the water column. And these two guys will suffer a lot, as you will see, from the anoxic condition. And this Rotaliporridae will disappear totally. This is really the group got extinct during this time. The one which are close to the surface, opportunistic guys, smaller ones, you will see that they will partly survive. So let's start more or less with the installation of the anoxic condition. So you start to develop anoxic condition in the seafloor, and well, it may lead, if you have this disoxic bottom water, you will selectively remove the benthic taxa, which are not very tolerant to low oxygen level, and cause the demise of the deepest dwelling planktic foraminifera. This one here, Rotaliporrida greenhornensis, will disappear. So this one is out. And well, by the transgression, you develop the oxygen minimum zone towards the surface. So, well, this you increase more or less the oxygen minimum zone, and what happens here? You have this expansion of the oxygen minimum zone will lead to the demise of the deepest dwelling planktic foraminifera. This guy, Rotaliporrida cushmani, and this is clearly an event that you can find almost everywhere in the world in the same time. So this is really a global anoxic event. And you can see also that, well, on the seafloor, life is more and more difficult for the non-tolerant benthic foraminifera. Afterwards, you have a maximum of anoxic condition, a very intense anoxic condition, and a big part of the column water is affected by the anoxic condition. And almost all the foraminifera, apart from the very, very surface-dwelling foraminifera, the name is, this foraminifera is well known to survive to this kind of environment. These are Edgerbella. Edgerbella is surviving, and you can see also that the benthos is very reduced to a few disoxic-tolerant species. And what happens here, before you have hyaline foraminifera, meaning that these are the foraminifera, in order to build the shell, they are precipitating calcite, okay? And here you have only agglutinating from nifra, meaning that in order to build their shell, they just picked some quartz grain, some grain all around, and in fact, their shell is made of grain. In order, and they are not able to precipitate any more calcium carbonate in enough quantity in order to really precipitate a real shell. And this has something to do clearly with oxygen, but also the fact that the pH, due to the large amount of organic matter and the large amount of CO2 into the atmosphere, into the water, may have lowering the pH for a while. And in this case, this is clearly the end of the story. So, well, this is how it works. So clearly, you can see that for the plankton from nifra, really the deep driller, the guys we have to go down during the life cycle are clearly going extinct during this time. Okay, and only that one are surviving. Okay, so now, what would be the scenario for these events? Okay, we have seen here different parameters varying. And what we have seen here, that we have a lot of oceanic crust production, sea level high, temperature will increase, delta C13 peak, higher productivity, and here you have a peak in strontium 86, 87 at the beginning and after a decrease, meaning volcanic activity, and a lot of annexia and a lot of atmospheric sea level. So it means that probably you have a disruption of the biosphere during this period due to trace metal release, sea level transgression, and disruption of circulation pattern. So you have a warging, an increase in CO2, a runaway greenhouse climate will increase also productivity, contributing to anoxia and mass extinction. And this greenhouse was probably put in reverse. It's the famous Gaia hypothesis from the book of Lovelock that I just explained yesterday, by the removal of the carbon from the atmosphere reservoir into the sediment reservoir, into the black shale. This is the way that you put an end to this perturbation of the carbon cycle, okay? And this understanding is quite important because, this is more or less what we have now, increasing CO2, and the main question is how to put this increasing in reverse, if it's not too late. Okay, but now there is one question still that we have to discuss. This is the problem of the productivity. And here I just want to spend a few moments about this crucial element for life, phosphorus. And I want to show you, in fact, that phosphorus play a role, a very important role for during this time, especially may explain also why the productivity was higher and higher, and why, if I just go back, yes, sorry, for a while, okay, no, it's not nice, oops, yeah, now I will take another one, sorry, in fact, why, in fact, the productivity were increasing, and after, apparently, the level of productivity was high for a few 100,000 years. And how do you sustain the productivity in this case? And phosphorus here has a crucial role to play. Okay, so now, in fact, what I want to show you, it's an example of feedback. You know what is more or less, let's say, the mean of a feedback, positive feedback, negative feedback? loops. Okay, it's not very complicated. In fact, if you have negative feedback, it means that you will accelerate the process. A good example, for example, if you have volcanic activity, you create the CO2. If you create the CO2, you induce a warming, and if you have this warming, if you have ice, the ice will melt, so the albedo effect will disappear, and you will accelerate the warming, okay? So this is a negative feedback, meaning that you accelerate the processes. And positive feedback is the contrary. You stop the processes, okay? Meaning that, for example, if it's very warm, you have a lot of greenhouse effect, you increase the productivity, so you have the sequestration of the carbon. If you have the sequestration of the carbon, you will draw down, you will have less CO2 into the atmosphere, so you will stop the warming. Okay, this is a positive feedback loop. And this is very important because all the Earth system is more or less following this kind of feedback. And the knowledge of this feedback this is a quite complex thing, but it's very important to understand, especially how we actually accelerate more or less, how we are really in a very, very, let's say, negative feedback loops, actually. Because you are really increasing the CO2, we are melting the ice, we have no more albedo effect, we have some permafrost with a lot of methane coming into the atmosphere. So what we did is to accelerate the greenhouse condition. This is really a negative feedback loop. And more or less to go out and to get more or less a positive one will be very difficult. That's why this example that I just showed you during all this week are very, very important to understand more or less how the Earth is actually functioning. So, and this is really the main topic. You use the past in order to try to understand the present. Okay, so here you have this kind of fluctuation where you have volcanism, tectonism, CO2, temperature, rainfall, nutrient runoff, primary productivity, black shale. Okay, and note also that the volcanism can be also submarine and can also accelerate the production by delivering trace metals via submarine currents. This could be also a case. So, how do we test this model? How do we test this very nice negative feedback loop? Okay, for the volcanism, well, we can measure in a section the metals from the hydrothermal origin, from the ridge, from the volcanism. We can measure the strontium isotope. I said when strontium isotopes are high, the ratio is high. This is mainly alteration of the continent, so a lot of greenhouse condition. And if it's pure volcanism, this will be the values will be less. Change in productivity, well, you can do quantitative biostratigraphy. You can count the foraminifera, the nanofossils, and see how the family are more or less quantitatively evoluting, because they have different kind, different way, different paleobiology, paleoecology. So we can measure the organic matter, the chain productivity. And the continental runoff, well, we can do several things, use elements in order to infer the increasing or decreasing alteration, detrital input, and the clay minerals abundance also may also be a very nice tool that I am using quite a lot in order to infer climatic change from, for example, arid to humid climate, or inversely. And well, there is a proxy which is quite interesting, could be quite independent for all this above. This is a phosphorus, because phosphorus, well, is clearly will increase if the continental runoff increase, because I remember you that the phosphorus as the origin is only the weathering of basement rocks, mainly granites. Some minerals like apatite have a lot of phosphorus, and this phosphorus will be delivered to the ocean afterwards. But the phosphorus also may also provoke a change in productivity, and that's why it's so important. Okay, so here I just show you, this is quite a busy diagram, but this picture is quite important. This has been published by Carl Fulmy some years ago. And what he did, in fact, was to measure here different curve as you want, as you can see. But this one, well, we took this from the literature. This is the long-term sea level change. If we start on top, okay? Here, this is the average carbon, organic carbon sedimentation. This is average calcite carbonate sedimentation. This is the atmospheric CO2 that you have here. This is the delta C13 here, and this is the phosphorus here accumulation. Okay, and here, what you can see here's the different points which correspond to some anoxic event. So what you can see here first, interesting things, that if you correlate this curve here, this part of the curve, there is quite a good correlation with the sea level. So phosphorus increase when sea level is increasing, but there is also, so at some point when you have really the anoxic event, you can see that phosphorus is decreasing. It's normal. Because what I said at the beginning, that phosphorus cannot be retained in under anoxic condition, because phosphorus is fixed to oxide. So if you have really anoxic condition on the seafloor, the phosphorus is unable just to stay into the sediments and will be released again and again in the water column. So yes, it means that it will sustain the productivity for a while at least. And what you can see here, that clearly there is a tendency, general tendency to have some correlation between that. But after, interestingly, if you see the sea level here is decreasing around, let's say, 30 million years, and the phosphorus here is increasing. So it's a little bit, it's exactly the reverse. So there is two modes here. There is one mode which is the Cretaceous mode, way, where phosphorus mainly correlate with sea level high and up and is low during black shale, but this is for another reason, due to the fact that you cannot fix phosphorus under reductive condition. But here, after in the upper tertiary, up to now, you can see that this is the contrary. Difficult to understand. So here, this is an example of the feedback that I want to show you. First of all, let's see what happens during more or less from 160 million euros to 32 million euros. So if I just go back, let's see what happens during that part where phosphorus is generally linked to sea level change, for example. Okay, so this is linked to this kind of quite complex, but in fact quite easy to understand. After 1 week, you will understand this quite easily. This is the way, in fact, feedback, this change of feedback, which led first, you have a warming, and you have a higher precipitation rate, you intensify the biochemical weathering, you increase the availability of phosphorus, you increase the productivity. If you increase the productivity, you increase organic carbon burial relative to carbonate burial carbon. You have a positive delta C13 shift, and finally, you increase the drawdown of CO2 by sequestration of this carbon. So if you decrease the CO2, you decrease the greenhouse condition, and you decrease the biochemical weathering, and you have lower productivity, and you increase the carbon burial relative to organic burial, and you get a cooling and sea level fall. And you put more or less in reverse these things. So you have an acceleration here. This is a negative feedback, and after a positive feedback, which will stop this warming. Okay, and now what is the situation from 32 to 0 million, to the actual, to the present? It's a little bit different here because, well, what you get here, you have a cooling, a sea level fall, and a glaciation. So you will intensify biochemical weathering, you will increase the availability of phosphorus, and after you will increase the phosphorus burial, and you will increase the drawdown of the CO2. And this increase drawdown of CO2 will lead to a further cooling. So here, in fact, well, you accelerate this process. And this is a way Van Karlfelmy was explaining the, we'll go back, sorry. Oops. The difference between these two curves, the fact that here you have quite nice evolution between sea level high, greenhouse, increasing carbon perturbation, and so on, and this nice correlation stop here. And what you have as an event here, 32 to 40 million years ago. What happens on Earth? In India, for example. What do you have in India? That's it. What happens globally? Huge tectonic event. India is, yes, is colliding with the Himalaya, with Asia, and is creating the Himalaya, okay? And it's the same with Africa. Africa, the acceleration of the tectonic activity is also more or less date from, let's say, the last 35 million years ago. So it means that, well, you, by this way, what happens? You have a lot more, well, first, very high mountain, a lot more weathering of silicate, and this weathering of silicate, as I explained at the beginning, will promote, in fact, the drawdown of CO2, because when you weather the feldspar, for example, into a clay, what you will take 2 molecules from the atmosphere of CO2, 2 molecules of CO2 from the atmosphere. And after, generally, by carbonate production, you draw down 1 molecule. So you have a sequestration here. And just think that suddenly, 30 million years ago, you have 2 phenomena, a huge uplift of Himalaya, alpine, so leading to a huge erosion. And moreover, since you draw down the CO2, you have more and more glacial. And this glacial will grind the rocks. And if you grind the rocks, especially apatite, from which contain the phosphorus, you will get finer and finer minerals, okay? And so it means that the specific surface of the minerals will be bigger and bigger, more reactive, because you have a lot more particles. And you have more reactive, you have more weathering. And if you have more weathering, you draw down the CO2. So that's why you have these 2 differences between these 2 feedback loops. The one concerning mainly the Cretaceous, and the end of the Tertiary. And this one will stop here, and this one will go to a further cooling, okay? And, well, it means that actually this latter, this one, is no more effective, because we are putting too much CO2 into the atmosphere. And the presence of mountain chain, the fact that we have glacial are not more very effective because we are melting the ice caps, we are melting the glacial, and so these things here is no more evident, and these things is starting again, at least up to here. Now the main question is how to do that. It's not very easy, especially at human scale. But we'll talk about that Thursday and Friday. Okay, now a little bit to finish the afternoon. I will go to show you some section and show you more or less what happens in that section. What are the indicator, the tools that we can use to show that phosphorus and alteration play a big role here. So these are the section that all these data are coming from PhD students that I had in 2002, 2003. Just finished in 2003, Heidenmort. And Heidenmort was more or less studying all these sections all over the world. As you can, we went to a lot of places. In Mexico, we went to Venezuela, we went to Brazil, we went to Morocco, a lot of places in Europe, but also in USA. So we will see a different section, and first we'll start to look to that section, which is located close to Denver in USA. And here during this time, this was more or less the Atlantic here, and there was Western Interior Seaway from the Atlantic to the Boreal, the Pacific, higher up, okay? And this section is located here, and well, this is a very good section. Why? Because we have a nice biostratigraphy linked to the planktonic foraminifera, and we have very nice, okay, yeah, I will show you this here, if it works. And we have a very nice, doesn't work anymore, again, more. I don't know why it stopped, because he's not. I'm maybe a little bit far away from the screen. Could be. I will use maybe that one. Could maybe work a little bit better. No. Okay. Well, it doesn't matter. Sorry for that. So I have to go back. Okay, so if I'm starting again with that one, we have a very nice biostratigraphy, and here, for example, you can see the disappearance of this deep dweller, the deepest planktic foraminifera, at the starting point of the black shell deposition. And you can see the very nice positive shift. But what you can also see that this positive shift here is making some kind of a plateau, more or less indicative of you maintain in high productivity during quite a lot of time. And the very good things, good news here, is that we can have also absolute dating, because in this core Pueblo, this North American section, we have a lot of bentonite layers, which means that we can date, absolutely date by argon and zircon, dating these ash layers. And by this way, we can date also the biostratigraphy, and we can date all these peaks here, the delta C13, because these changes are global. They are global in the ocean, so you can correlate them. So it means that you can, for example, correlate Colorado with England, okay, where we don't have any bentonite, but we have the delta C13, and we have the biostratigraphy. So this is very important, because by this way you have an idea of the timing and the tempo of this event. Another thing which was quite important in Pueblo is the fact that we run also, well, first of all, this is paleography here with the situation of this Western Interior Sea. And here you have the mountain chain here. And this is from where that you get the volcano we're providing of the ash layers that are present in that section. And here you can see very interesting things which will bring you an answer about the acceleration, the intensification of the greenhouse effect. We run some stable isotopes, oxygen stable isotopes, on some very tiny foraminifera, which are generally considered as subsaline foraminifera living at the surface. And interestingly, you can see that these values are very, very negative. So in order to obtain very negative values of oxygen isotopes, well, you can do two things. You can have a diagenetic modification of the calcite, which will be replaced and generally have more negative values, or you can say that it's a question of salinity, because oxygen O18 oxygen isotopes is varying from the temperature but also from the salinity. If you have fresh water input, your values will be very, very negative. And it's exactly what we see here. You can see here that we have -10, 8. And interestingly, these guys here, which are typical for, let's say, subsaline water, are showing each time some peaks when you have mostly freshwater input into this Western Sea. So it's important because it means, especially before, because looks, the black shale are here, and these things is occurring before, but before you have an increased hydrological runoff at the onset and before the excursion. So it's important because it's a key point, because it means that here you have a proof that you increase the greenhouse condition, probably due to volcanic activity, before the onset of and the deposition of the black shale. So this was quite interesting to have a look on that section. Another things here, I don't want to go into detail, but it's another interesting things that show also that there was a change, in fact, in organic composition. This is a TOC, so this is values for the organic matter going up to 3-4% during the event, which is here. But below, the interesting things are these two curves here. The red one, this is organic matter of terrestrial origin, of marine origin. The high hydrogen index is indicative of a marine origin, and the blue one is oxygen index, which is indicative of terrestrial origin. And you see that when you have the large freshwater input, you have more organic organic matter coming from the land, which is normal. If you increase the riverine input, you increase the runoff on land, you will get more organic matter of terrestrial origin. And on the contrary, when you start to have the delta C13 shift, which is just here, you can see a shift from a dominant marine organic matter, black shale, to compared to the terrestrial. So it means really that the starting point was a huge terrestrial flux during this time. And after, there is also quite interesting things. We have now calculated the phosphorus accumulation during this time, okay? So it means that during this time, you have here, this is a stable isotope curve, delta C13. So you can see nicely that you have this onset, the peak, and after the plateau, meaning that you sustain here high productivity. And when you do that, and you put the phosphorus here, look what happens. It's, does it work? Oh, not yet. Okay, so here what you see, here's, this is the total phosphorus mass accumulation, and this thing is definitely not working. Okay, well. Okay, so you have here, well, the starting point, and at the onset, you can see that you have a lot of phosphorus coming, and after, you have a decrease of phosphorus when you get the plateau, okay? So it means, here, an important things, we have seen that we have a lot of freshwater input, especially before. After, we have seen that we have sometimes also more digital input, and we see that the phosphorus as a maximum at the beginning, so a maximum of input, probably a maximum runoff here, meaning that you have greenhouse condition, and after it decrease. Okay, so this is a very important point because it may explain why you boost the productivity because you boost the production of phosphorus and the delivering of phosphorus into the sea. Another things which is also very interesting for the same section, it's always in USA. Well, you can see here that this is again the delta C13, and here we use a kaolite. So kaolite is clay minerals, which is typical for, let's say, humid tropical condition. And kaolite here, you can see that at the just up to the onset is increasing with a maximum, and this maximum corresponds to the maximum of phosphorus that we have just seen. And after, kaolite is decreasing. And this is probably linked to the change, a climatic change towards that. So what we have is, first of all, high kaolite content with a maximum at the onset of the C13 shift. We coincide with the maximum of phosphorus. And after, kaolite is mainly absent, weakly present in the shell. This coincides with more normal salinity and probably higher seasonality, drier condition. So this is change. And this change is probably linked to the perturbation of the carbon cycle. Afterwards, if we compare this to the climatic maps that you have here, well, generally you can see that for the Cenomanian Turonian, we had, well, cool temperate, there is no ice, it's just too warm for sure. And we have some warm temperate here, tropical condition, and sometimes a little bit of aridity. So you can have this kind of fluctuation. Okay, so it means that, okay, we have here some clues which are very important. Increasing runoff at the onset of the change, of the perturbation, increasing phosphorus at the onset of perturbation, maximum of kaolite, maximum of humidity at the onset of the perturbation. Okay, now let's go to Italy in Furlow, and let's see what happens here. These are deeper setting. Clearly in US, the setting was not so deep. It's hemipelagic. Here it is very deeper. This is a picture that I just show you. And in Furlow, this is quite deep. So the problem is that during this event, it's probably linked to a lot of organic matter. Preservation of plankton foraminifera is quite bad. So we have to use the delta C13 on organic matter. But we have exactly the same peak that you can see in US. So we can correlate these peaks and we can put some age, okay? And it's what we have done. At what we have done, this is quite interesting here. Now we can compare the phosphorus accumulation rate for all this section. And what you can see here, that this was a Pueblo acceleration of the runoff, maximum of phosphorus at the onset of the peak. And here you can see also a maximum phosphorus at the onset of the peak. And you can see it also in Italy and in Spain, always at the same place. And this is quite important. And it means that this is a global event, okay? And after, in all the section, you can see that you have a decrease in phosphorus into the sediments. We have less phosphorus almost everywhere, okay? Maximum accumulation of phosphorus at the base of the shift, close to the first isotope peak. But you can correlate in all the sections from US to Spain and Italy. Okay, how do we do that? How do we understand the behavior, the distribution of the phosphorus? So it's we propose following model here. First of all, you have huge volcanic activity. So you increase the CO2, you increase the temperature. And you create an oceanic thermal expansion. You will have also transgression linked to this increased crustal production, increased volcanic activity, and so on. And so what you get is an inundation of epicontinental shelf and the formation of new coastline, meaning a lot of erosion, remobilization of nutrients, and increasing also weathering. So this remobilization of nutrients from newly formed seas will boost, more or less increase the phosphorus accumulation. But in the same time, on land, you have higher precipitation, more runoff, more freshwater input, as we have seen. You get this stabilizer top very negative, you get the kaonite. So you have more phosphorus coming also from the continent, which will also increase the phosphorus accumulation. So you get increasing productivity, and this will boost the productivity and lead to anoxia. Okay, here you have a coupling between, at least the beginning, and carbon and phosphorus, but after, as I said, you have a decoupling, okay? You start to increase the phosphorus here in this curve, okay? This is the phosphorus at the onset, and after you have the decrease. So we have to understand that. And here, this is clearly linked to the fact that phosphorus cannot be retained under anoxic condition. And we can propose a model like that. You first enhance the productivity, and you have a peak in phosphorus corresponding to this peak in alteration, riverine input, runoff, increasing runoff. But afterwards, the sediments become completely anoxic and is really unable to retain phosphorus due to the fact that the sediments and the seafloor is completely anoxic. So, in fact, what you have, it's a recycling of phosphorus. So phosphorus will be released again into the mass water, and it's a positive feedback which will sustain the productivity for a while. And this productivity, you can see here, as you sustain this productivity and you create this plateau here, because you recycle phosphorus and you boost again and again the productivity. How do you stop that? This is probably to the fact that, well, you accumulate the carbon by sequestration into the black shell, and you change the climate condition towards more arid, cooler condition, and less humid. And it's exactly what the kaonite is saying. Remember, the kaonite was very abundant before and the onset, and after, when, especially during this plateau, kaonite is disappearing because the climate is changing, because the carbon cycle is changing. But here the phosphorus is very important because it may explain that during anoxic condition you can sustain the productivity forever. And I think it's very important, actually, we have a lot of dead zone all around the world into the ocean, and we are putting more and more phosphorus. So it means that this phosphorus that we are putting as nutriment as nutrients linked to the fertilizant. And there is not only the phosphorus, nitrogen is also a problem. Will be not fixed into the sediment because you have anoxic condition, and will sustain this productivity and really lead to some probably catastrophic event and dead zone into the ocean. And interestingly, we see exactly the same thing here in Egypt, for example, where you can see that these are completely different, let's say, paleogeographic and environmental condition. We have deepening here, but this is quite shallower. And this is a delta C13 curve with a nice increase. And you can see again, you have a peak in phosphorus preceding the onset, and after no more phosphorus during all this excursion. Meaning that here maybe also phosphorus is sustaining the productivity and explain more or less the persistence of high values of delta C13. And if you see the kaolinite, exactly the same thing, increasing kaolinite and after decreasing kaolinite, meaning that we have a change in climate here. So you can really export this model in a lot of location in the world, okay? And to the end here, we can say a few things about the models, and these things we have published that things in geology. This is a general explanation of what I just say. There is 4 steps here. First of all, you have this step 1, and during this step 1, you have generally what you get. This is a stable delta C13 values and stable phosphorus values, low organic matter accumulation. And after you change this situation, you increase the greenhouse condition, you have more riverine influx, you have more phosphorus flux, and you get an increased productivity and a lot of phosphorus coming just at the onset. And this phosphorus will be generally released in the next steps, because more or less you cannot really fix the phosphorus under anoxic condition. So the phosphorus will be recycled into the water column and maintain high productivity for a while. And at the end, you go back to normal condition due to the fact that the overall nutrient budget of the ocean is dropping, because you move from humid to more arid condition, and ocean return to more oxic condition and less detrital fluxes. So I think it's a nice illustration of feedback loops. Maybe a little bit complicated, but it's really interesting, because it shows you really that this kind of perturbation can be really sustained for a long time if phosphorus is delivered really over a long time. And I am a little bit afraid that it would be the case maybe in the future. So that's why this kind of model are quite important. But on an overall view, here this is a comparison on the long term here, all for the Cenomanian to the Turonian. In fact, there is 2 things that you can see here. There is linked to the sea level, general overall P decrease from the Cenomanian to the Turonian, which is interrupted by generally a change from to more humid climate, and you have this increasing phosphorus just at the onset. So in fact, what you can see, there is a long-term phosphorus decrease, which is probably linked to the fact that you increase the sea level. So the source of the detritus is far and far away. But during this increase, you have this episode of more humid climate, which leads to this fluctuation in phosphorus that you have here here, and here, and here. And after this phosphorus is recycled during the anoxic event, and will explain why you have a so long plateau here, which indicate high productivity. Okay? So it means here that, in fact, this perturbation of the Snowmanian Turonian is really linked to fluctuation in productivity, is really linked to perturbation to the carbon cycle, and this perturbation to the carbon cycle has been sustained by this phosphorus release because phosphorus cannot be fixed under anoxic condition, which is quite a problem. Okay, now there is another question that we can discuss just for a while. This is the question of the preservation versus the productivity. Because here in this model, what I was trying to explain is that, okay, you have a feedback loop which will increase your phosphorus content and which provoke this increasing productivity and will sustain the productivity, so you have this acceleration of the carbon cycle and so on. And you accumulate organic matter. But this accumulation of organic matter can be due only to increasing productivity. And here what we try to do is to use some kind of modeling because we know that we have generally a lag between the total P accumulation that is in 13 excursion. We can see this lag in several localities, and it means that, it looks that, in part you have productivity, but you can see that this decrease in PMR activity can also lead to some increasing preservation because you have more and more anoxic condition. So the question is the following: well, okay, part of organic matter, big part of organic matter at the beginning is linked to increasing productivity. There is strictly no problem about that. And it's linked to this change in climate, increasing greenhouse condition, increasing alteration leading to more and more phosphorus from land. But here what we try is now to model and to see if especially at the end of this episode you don't increase a lot more the preservation than the productivity. Because clearly when you have anoxic condition, preservation may play a role. And here what we have done is to use a very simple model, very, very simple, because from, in fact, what you can do, it's a model that we use for lake mainly, from the total organic carbon data C13, you can more or less try to measure the total organic carbon which would be produced by productivity and compare it to the measurement of the Cretaceous tertiary mass extinction. And we'll speak quite a lot about India, clearly, because a lot of the main part of the scenario, or part of the scenario, is occurring in India. So I will show you quite a lot of data coming from India. Probably it would take quite maybe not all the days. And after, I will also show you the PETM, and here again, we will also take samples from India, a little bit less than for the KT boundary. And by this way, Friday morning, we can end with, let's say, very probably the Anthropocene, and start a discussion in the afternoon. So I encourage you to read the papers. And somebody sent me an email yesterday saying that it was difficult to read for the color. So if you want, you can ask to Syed to give you a PDF version that you can read on your phone. You doesn't need a computer for that. If you want to see, because I saw that the graph are sometimes difficult to read, especially the difference between the methane in blue and the carbon in green. It's not so easy. So just ask him. He can send you that to your email and or by WhatsApp for at least the pages where you have the graphics. Okay. I think I will end here. Thank you very much, and see you tomorrow.